Hello, welcome back. In this segment, I want to introduce you to the concept of generator. Okay. For example, take this group Z star 11 that we have been playing with. This first row is 1 power 1, 1 power 2, 1 power 3, and so on until 1 power 10. Okay. Second row is somewhat interesting. 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, all the way until 2 power 10. So the element 2 is a generator because it generates all the elements from 1 through 10, right? 2 power 1, 2 power 2, 2 power 3. All if you look at all of the elements on this row, you see all of them are distinct. It covers all the elements from 1 to 10. So 2 is a generator. Okay. Similarly, you will find 6 as a generator, 7 as a generator, 8 as a generator. Okay. Let's look at some other numbers other than 2, 6, and 7. Let's take number 3. This is 3 power 1, 3 power 2, 3 power 3, 3 power 4, 3 power 5. Okay, but there are some interesting things we can learn still. Even though 3 is not a generator, it's still interesting. 3 square is 9. 3 cube is 5 in mod 11, right? And 3 power 4, what is 3 power 4? 3 power 3 is 5. So 5 into 3 is 15. 15 mod 11 is 4. Okay, that's why you see a 4 here. And 3 power 5 is 4 into 3, 12, which is mod 11 is 1. Okay, so what is so interesting about this set of numbers is that if you multiply any two numbers in the set, the answer is also within the set. For example, take 3, multiply it with 3 square, you get 3 power 3. So it's called closed property. Okay, a set is closed to, if you multiply two numbers, the answer is within that set. And take any arbitrary group element G and compute G power 2, G power 3, G power 4, all the way until G power I, where I is the order of the group element. Such a set actually forms a subgroup. Okay, what it means is that, for example, take this set again, 3, 9, 5, 4, 1. If you take 3 into 9, 3 into 9 is 27. 27 mod 11 is 5. You see 5 is part of the set. And you can also see 1 is the identity element. You can take any two elements, you multiply, the answer will be within this set. Okay, you have to do all the time mod 11, of course. That's how multiplication is defined in this group. What is more interesting is also that inverse. If you take 3, if you multiply 3 by 4, you get 1 in mod 11. And that means the inverse of 3 is 4. What about inverse of 9? Inverse of 9 is 5. 9 into 5 is 45. 45 mod 11 is 1. What about inverse of 5? Inverse of 5 is 9, of course, because it's commutative. In the sense, inverse is commutative. 9 inverse is 5 means 5 inverse is 9. Okay, what about the inverse of 4? Inverse of 4 is 3, because the inverse of 3 is 4. Anyway, you got the inverse, and associativity is true by the way we define the multiplication. And we have identity. So all the properties of a group are satisfied. That's why we call this set a subgroup. Such a set is called a subgroup of the group G. Okay, the group G is all the numbers, in this case, from 1 through 11. That's the reason for the Z star 11, right? Z star 11 is the group. Generator generates a subgroup. Okay, sometimes the generator generates the entire group. Sometimes it's only a subgroup. Okay, usually when people say generator, it generates the entire group. But I just wanted you to be aware that this notation means you're considering G power 1, G power 2, all the way until G power I. Okay, let's prove this more formally, that the set is indeed a subgroup. So for that, I have already prepared the proof. So we consider a finite group G and a group element small g with the order I, meaning G power I is 1. That's how we define the order of the group element. And we define a set, and which is denoted with this angle bracket G and another bracket. Is nothing but G power 1, G power 2, all the way to G power I. And we need to prove that this set is a subgroup of the group G. One of the earlier segments, we argued that in order to prove a set is a subgroup, it is enough if we show that set is closed. Okay, so I'm only going to prove that the set is closed. Then that is enough for us. Let's pick two elements from the group generated by the generator G. Let's say A and B are two elements. What it means, A must be G power X, B must be G power Y. Otherwise, A, B will not be a part of this set. Okay. What is the multiplication? You multiply A times B, which is nothing but G power X plus Y. But we proved in the previous segment, in order to compute G power X plus Y in the group, it's enough to compute G power X plus Y mod I, because I is the order of the group element G. Okay. But what about this value, x plus y mod I? It must be a value less than I, right? When you divide a number by I, the remainder cannot be more than or equal to I. Okay, that means x plus y must be less than I. That particular power is a number which is clearly present in this sequence of numbers. Okay, if you look at the superscript g power 1, g power 2, g power I, that means we are going all the way from 1 to I. You may ask, what happens if x plus y is same as I? Okay, can that happen? It could happen, right? In that case, what will be the answer? In that case, it will be g power 0. But there is an interesting fact. G power 0 is nothing but g power I, right? Because they both are equal to 1. Okay, we proved this fact that if you take any two elements and you multiply, the exponents can add because of the rules of exponent. And instead of computing g power x plus y, we will be computing g power x plus y mod I. Since x plus y mod I is less than I, we know for sure it is one of the group elements. Okay, if x plus y mod I is 0, it's same as g power I, because g power I is same as g power 0 equal to 1. So we covered that case as well. All right, so we have proved the fact that if you take any group element and consider the set spawned by that particular group element, that set is actually a closed set. Therefore, it is a subgroup. Closeness is enough. If you prove a set is closed, that implies the set is a subgroup of a finite group. Thank you very much. That's all.